other is that a nucleus, as you know, is a very small thing, and we know very little about it. I had the opinion for a long time that if we knew more about the nucleus, we'd find it was a much simpler thing than we suppose. I am always a believer in simplicity, being a simple person myself.
Ernest Rutherford, one of the most remarkable scientists of the last century. He practically invented the vocabulary we use to describe anything in nuclear physics today. But arguably, one of the most significant legacies of Rutherford to the world of science was his ability to recognize, nurture, and support the curiosity of his students, enabling them to make great discoveries of their own. Two such students were Ernest Walton and John Cockcroft. The work of these men laid the foundation for unlocking the most powerful secret of matter, the boundless energy contained in the nucleus. In 1932, Cockcroft and Walton in Rutherford's laboratory built a machine that could shoot a beam of protons at very high speeds.
So the first time we were able to make an experiment which is of the type of the experiment we can do here. It means using an accelerator was this experiment performed by Cockcroft and Walton. And what they did, because before we were using a radioactive source to have a high energy particle to induce a nuclear reaction. But what Cockcroft and Walton did, they gave this energy to the particle with a small accelerator, with a small cyclotron. It was in 1932. And the experiment was to make a proton beam with this small cyclotron and to bombard a lithium target. And then the lithium decomposes it's a nuclear reaction, and the proton plus the lithium would eventually give 2 alpha particles.
The Cockcroft-Walton experiment demonstrated for the first time a concept that Albert Einstein had proposed almost 30 years earlier.
If you take nucleons alone, if you put them on a scale, for example, just measure the weight, okay, good. If you put them together, if they are bound, for example, if you take a proton and a neutron, if you put them together and then put them on a scale again, what you see is this nuclei, these 2 nucleons together bound are lighter than the nucleons together. Why? Because they give a little bit of their mass and they convert it into binding energy. So what happens? Some mass have been converted into energy.
The equation E is equal mc squared, in which energy is per equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy. This was demonstrated by Cockcroft and Walton in 1932 experimentally.
The media reacted to the experiments similar to those done by Cockcroft and Walton with enthusiasm. Scientists, however, were less optimistic.
These transformations of the atom are of extraordinary interest to scientists, but we cannot control atomic energy to an extent which would be of any value commercially, and I believe we are not likely ever to be able to do so.
By 1938, most scientists were shooting neutrons at uranium, hoping to find elements heavier than uranium that would be of scientific interest and perhaps some practical use. Leading the pack was a trio of scientists from Germany. Otto Hahn, his research partner of some 30 years, Lisa Meitner, and Fritz Strassmann. In July of 1938, Professor Meitner, who was of Jewish descent, had to flee from Nazi Germany to Sweden. But Hahn and Strassmann continued their work. By about October, they were getting some very strange results. The elements they were observing were not new, but looked either like radium or barium. Hans wrote to Meitner in December of 1938, telling her about their puzzling findings. Her nephew Otto Frisch also a physicist at the Niels Bohr Institute in Denmark, visited Meitner just before Christmas, and together they worked out a startling explanation for Strassmann and Hahn's results. Here's how Frisch recalled the event.
When I came, she was brooding over a letter of Hahn. And then we sort of kept rolling this thing around and saying, barium, I don't believe it, there's some mistake. We couldn't chip 100 particles off a nucleus in one blow. It's fantastic, it's quite impossible for a single neutron to do that. And I still don't know how we got to the concept of fission, but I remember Lise Meitner drawing a dotted circle on a piece of paper and saying, couldn't it be this sort of thing? We walked up and down in the snow. I was wearing skis, and she said proudly she could get along just as fast on her feet, which she did. And gradually we came to the idea that perhaps one should not think of the nucleus being cleaved in half as with a chisel, but rather that perhaps there was something in Bohr's idea that the nucleus was like a liquid drop.
In terms of fission, a really nice way to think about it is to think of a liquid drop. You have a liquid drop, and what happens is, on absorption of a neutron, you actually excite this drop to such an extent that it actually pinches off. So you have what we call a necking behavior, where you have this like a balloon that necks, and then at some point it actually pinches off completely, and you have two fission fragments that are given off, and in addition to that you have the emission of neutrons. So that is how you can visualize the fissioning, for example, of the uranium-235 nucleus.
Finally, Meitner and Frisch understood what happened in Hahn and Strassmann's experiments. The neutron shot into uranium had been captured by the uranium nucleus. This caused the nucleus to change shape, vibrate, and come apart entirely. This was not the usual slight transformation of a nucleus seen up till now, but did fit neatly with a recent theory of Niels Bohr's. He believed that a nucleus behaves like a liquid drop, and a liquid drop hit hard enough might stretch until it broke into two. Now, if that happened to a nucleus, a lot of energy would be released, far more energy than had been seen in any process up until then.
Now, if you take the uranium-235, these 235 nucleons together, again, we put this uranium-235 on the scale, it's very heavy, then you cut it, and you take the two daughter nuclei, you put them on the scale again. What you see is the uranium-235 is a bit heavier than the two daughter nuclei together. What happened is the binding energy I was talking earlier with just two simple nucleons. The binding energy, of course, in the uranium-235 is massive, because all these 235 nucleons give a bit they give a bit of energy to be together. They are bound with this energy they give, the bit of mass they give to be bound. Now, depending on the nucleus, the binding energy is a bit different. The nucleons give more, a little bit more in this nucleus because they are 235 in the uranium, or 135 in these two daughter nuclei. And the difference of binding energy when the uranium fissions, this difference of binding energy is found in kinetic energy.
Frisch continues with his story as follows.
My recollection is that when I came back to Copenhagen, I found Bohr just on the point of parting, of leaving for America, and I just managed to catch him for 5 minutes. I hadn't spoken for half a minute when he struck his head with his fist and said, "Oh, what idiots we have been, that we haven't seen that before. Of course, this is exactly as it must be." And he added, "This is very beautiful, and had we written a paper."
When he got home, Frisch devised an experiment that proved Meitner's guess. He wrote a second paper on his results that he submitted with the first one.
They were both sent to Nature at the same day, but Nature published one after the other. And I might still mention that the word fission occurs in the first paper and was suggested to me by an American biologist, William A. Arnold, whom I asked what you call it when a cell divides itself.
On the very same day that Frisch sent out his scientific papers on fission for publication, January 16, 1939, Niels Bohr's ocean liner docked in New York. Enrico Fermi, an Italian physicist and Nobel Prize winner, was on the pier to meet him. Bohr and Fermi were both attending a theoretical physics conference in Washington, D.C. that same week. A physicist close to Bohr, John Wheeler, remembers Bohr's excitement about the fission concept.
Bohr felt that he owed it as a responsibility to Frisch and Meitner that word of their work in progress and their concepts should not really be released until they had had the proper scientific opportunity to publish it. And it was not until the second day of the conference that an issue of Die Naturwissenschaften was handed to him, which had just come in, which had the work of Hahn and Strassmann. So then he could tell about it, and then of course everybody got started on the experiments.
The first order of business was to find out whether enough neutrons were released during a fission reaction to make a chain reaction possible. If this was the case, fission would have the potential to release more energy than it took to start the reaction. It wasn't long before scientific teams both in Europe and the United States found that neutrons do come from split uranium atoms and that a chain reaction was possible. Now people could begin to think about what to do with this new discovery. It was Enrico Fermi that 3 years later led a team of physicists to release the first nuclear chain reaction in Chicago, USA. Arthur Holly Compton recalls this historical moment.
We entered the balcony at one end of the room. On the balcony, a dozen scientists were watching the instruments and handling the controls. Across the room was a large cubical pile of graphite and uranium blocks in which we hoped the atomic chain reaction would develop. Inserted into openings in this pile of blocks were control and safety rods. After a few preliminary tests, Fermi gave the order to withdraw the control rod another foot. We knew that that was going to be the real test. The Geiger counters registering the neutrons from the reactor began to click faster and faster till their sound became a rattle. The reaction grew until there might be danger from the radiation up on the platform where we were standing. Throw in the safety rods, came Fermi's order. The rattle of the counters fell to a slow series of clicks. For the first time, atomic power had been released. It had been controlled and stopped. One of the things that I shall not forget is the expressions on the faces of some of the men. There was Fermi's face. One saw in him no sign of elation. The experiment had worked just as he had expected, and that was that.
Along with the fission fragments, I mentioned that you also have neutrons that are emitted. These neutrons can then be used if you have a controlled nuclear reaction to fission further uranium-235 nuclei. And in that way, you can have a chain reaction. Now, the chain reaction can be controlled, as in the case of a nuclear power station, or it can be a runaway reaction, as you have in the case of a nuclear weapon device.
Amid the excitement surrounding fission, Rutherford, quite unaffected by all the hype, continued his study of the nucleus in his famous Cavendish labs in England. In that same year, 1932, that Cockcroft and Walton released their incredible results, another student of Rutherford's, Mark Oliphant, discovered that not only could you make an atom split apart, but you could also make the nuclei of two atoms merge. He performed the first nuclear fusion reaction. Fusion, however, is best studied in relation to the stars.
So while fission is a process of taking a nucleus and splitting it apart, nuclear fusion takes two separate nuclei and joins them together. Now, you know from electromagnetism that for two nuclei to come together, they're going to have to overcome this Coulomb barrier. If we want to fuse two protons together, we're going to need an energy of about 400 kilo electron volts to overcome this Coulomb barrier. Now 400 kilo electron volts is actually quite a lot, because room temperature comes to only about 0.025 of 1 electron volt. If you think about this, the energy needed to ionize hydrogen, that is to rip off its electron, is only 13.6 electron volts. And at room temperature, we don't even have enough energy to do that. So when we talk about two protons needing an energy of 400 kilo electron volts, that's 400,000 electron volts. That's a great deal more energy than we just have on the Earth. In the stars, like the sun, however, you've got the added benefit of gravity to help give the nuclei enough energy to overcome their Coulomb barrier. In space, we have nebulae, which are giant clouds of gas, mainly composed of hydrogen and a tiny little bit of helium. Now, these are star-forming regions. These are where stars get born. What usually happens is this cloud of gas is sitting there quite happily, and a supernova or something nearby causes this gas to start collapsing together. So all the particles which were in gravitational equilibrium, once they start to move, they start attracting each other gravitationally, and they all collapse towards a central point. This is how a star is formed. Now, as this gravitational collapse happens, you get an increase in the energy and the temperature of this hydrogen gas, until the point where the atoms can overcome the Coulomb barrier and start fusing together. And that's when nuclear fusion kicks in. The temperature of the sun is about 15 million degrees, which means not only are all the atoms in the sun all positive because of the temperature they've been ionized, it means that you have enough energy to overcome the Coulomb barrier and you can do nuclear fusion. The first process that happens is that the protons, the hydrogen nuclei, fuse together to form what is known as a deuteron. That's a proton and a neutron. This reaction is actually very rare. The likelihood of this happening is about 1 in 10 to the power of 26 protons. Luckily in the sun, there are so many protons that this reaction can occur. Because of this beta decay, it's actually quite a slow reaction, and this is what stops the sun from blowing up all in one go. Next thing that happens is, now that we have a deuteron, we can fuse this with a hydrogen atom to form helium-3. Now, in each of these reactions, energy is released, sometimes in the form of a photon or with the beta decay. Finally, what ends up happening is we get two of these processes to form helium-3, and then the helium-3 can join together to form helium-4, which is normal helium, and 2 extra hydrogen atoms. So this is the basic reaction that happens in stars. You start off with hydrogen, and slowly this process converts that hydrogen into helium, and you let off about 26 MeV of energy while you're at it. This process can keep the sun burning for about 10 million years in the case of our sun. Bigger stars, because they're hotter, use up their fuel quicker, so they end up having a shorter lifespan. Once the sun exhausts its hydrogen fuel, it's going to start burning helium to keep itself alive. This helium is going to fuse together to form carbon-12. And the carbon-12 gets used in other reactions to form things like oxygen, nitrogen, magnesium, and other heavy elements. The sun continues to burn its fuel, producing heavier and heavier elements until it reaches a core of iron. Once that happens, the sun cannot burn anymore. In the case of our sun, the sun won't be able to hold up its gravitational force anymore, and it will collapse to form a white dwarf. It's a very dense star that's hardly giving off any light.
Admittedly, the way in which we have wielded nuclear power has not always been amicable. So the question beckons, where is nuclear physics taking us in the future?
The accelerator is the tool of the nuclear physicist. In most of the cases, you need a beam to induce a nuclear reaction and to be able to study the nucleus, because the nucleus, the energies of the binding energies of the nuclei are extremely high compared with what we know in chemistry. If you take a molecule, 2 atoms are bound together with a certain energy. But 2 neutrons in a nucleus are bound with an energy which is of the order of some millions times higher than in a molecule. So you need the tools to be able to investigate a nucleus. You need to disturb it, to give some energy, to put some excitation energy in this nucleus, or to break it, or to do something, to have a nuclear reaction, to synthesize a new nucleus, or and to study its features. I mean, its structure, how it decays, and all these things.
Nowadays, the one at CERN that they are building, the synchrotron there, we are talking about the first one, 1.2 MeV. Then you have to go to 1,000 MeV, you get to GeV. Then you have to go to 1,000 GeV, then you get to TeV. And the one that they are building in CERN now, which hopefully by the end of this year will come into operation, will be 7 TeV.
The ITER project, the ITER project, is a nuclear process, but it involves the fusion of atoms, the bringing together of atoms. And so it is technologically and fundamentally a different approach to generating energy. It is in its developmental stage at the moment, and a site has been selected for the ITER reactor. That's in Cadarache in France, and there's a multinational corporation on this project. And if successful, it may provide endless amounts of energy for the world.
One thing is clear. The discovery of nucleosynthesis provided humankind with a vast energy resource. Perhaps the hopes of most people with regards to how to use this resource can be summed up by the words of Enrico Fermi in a 1952 press conference.
It was our hope during the war years that with the end of the war, the emphasis would be shifted from weapons to the development of peaceful aims. Unfortunately, it appears that the end of the war really has not brought peace. We all hope, as time goes on, that it may become possible to devote more and more activity to peaceful purposes and less to the production of weapons.